Today we get into conditional probability, where things can get a little bit, I'm going to say tricky, I'm going to say non-intuitive. So non-intuitive is your gut is going to tell you, I know probability, I have a good idea what's going on, and then your gut is going to be wrong. And that's something called Bayes' formula. So the probability of two dependent events, if you have event A followed by event B, right? If they're dependent, the probability of B is written this way. Probability of B given that A has already occurred. So a simple example, I have 52 cards. What are your chances of getting an ace? This isn't hard. 4 out of 52. So you pick one. Did you win? No. So now another person picks a card. That card doesn't go back in. What are his chances of getting an ace? 4 out of 51. Makes sense, right? Because one card is taken out. And that's where this second part, the probability of B, given that one card is already gone. And so now our probability changes. Even though I asked the same event 2 times in a row. What's the probability of getting an ace? And then what's the probability of now getting an ace? Given that one's taken out, your probability changes. Now if we take that formula and do algebra with it and rearrange things, we get the following. The probability that of B given A is the probability of A and B, which just change the symbol to a word, divided by the probability of A. Now that also seems simplistic enough in its idea, because we just rearranged the formula. But now we can get into questions that ask, what is the probability of something happen given that something else has already happened? So I'm going to give you an example of where this can kind of blow your mind. Okay, I'm going to take a red dice and a white dice. And I'm going to roll the red one, and everybody sees that I rolled a 1. What are my chances of getting 7 in total with this second dice? 1 in 6. Does that make sense? Because what do I have to get on the second dice to get a 7? A 6. I got a 6. Yes. So it was a 1 in 6 chance, because that one, chances of getting a 7. Now if I roll both the dice, what are the chances of getting a 7? Okay? And it's true that it's still 1 in 6, but what would be, if I wrote out all the possibilities of rolling 2 dice, does it make sense? Oh, I didn't get it. Does it make sense that there's 36 possibilities? Maybe you've seen before making a chart of, well, let's do that chart, just for fun. That didn't happen to do anything useful. So rolling 2 dice, there's 36 possibilities. And how many of them are 7? 6 out of 36, so we get 1/6 again. And now I blow your minds. Ready? Ooh, I rolled 2 dice. One of them has a 1. What are the chances I rolled a 7? 1 out of 6. And this time, it's wrong. What? So when I roll 1 dice and I show you I rolled a 2, and then I say, what are my chances of rolling a 7? It's 1 out of 6, because I have to get a 5 on the next dice. When I roll both dice and show you, what are the chances I roll a 7? It's 6 out of 36, which comes out to 1 out of 6. But when I roll them and don't show you, and just tell you that one of them is a 3, what are the chances that I rolled a 7? Becomes conditional probability. It becomes conditional probability, and the reason we say that is because I've given you a condition, something you know, and the thing that I tell you gives you some information. When I tell you that I've rolled one of them a 3, is it possible that my sum could be 2? No. Is it possible my sum could be 3? No. Can you see that by telling you one of the dice is a 3, I can eliminate these for sure. What else can I eliminate? Could I roll a 2 and a 2 if I tell you one of the dice is a 3? No. What I've actually done is I've told you that it's either these numbers that I've rolled or these numbers that I've rolled. Does that make sense? When I tell you one of the dice is a 3, I reduce your total sample size smaller. Instead of having to consider all 36 possibilities, how many possibilities are there? What is the total? Because probability is favorable over total. There's only 11. Why 11? You can't count the 6 twice. Right? There's 6 here and 6 there, but that counts that 6 twice. There's only 11. And of those 11, how many are 7s? 2. So it's close to 1 out of 6, but not quite. And so by telling you, and I chose to roll a red and a white dice, because if I give you the white dice is a 2, then your probability is 1 out of 6. But I don't tell you which die had the 2. Then you have to say, the only thing you've given me information about is that one of these happens. That reduces my sample size to 11, and then my conditional probability is 2 out of 11. Again, is that intuitive? No. So what do some of our conditional probabilities look like? Box A contains 4 red balls and 3 green balls. Box B contains 2 red balls and 2 green balls. You choose 2 balls, 1 from each box. Find the probability that you choose balls of different colors. This is just regular probability at this point. So if we draw our tree diagram, yeah. Did I skip one? Things got mixed up? A lot? Okay. Okay. Back on track. This is where we're going next. Okay. Did I finish the slide before talking about everything on there? Yeah. Okay. Oh, I just didn't mention the keywords, but those are things that tell you something has happened before. Of the 53 staff at school, 36 drink tea, 18 drink coffee, and 10 drink neither tea nor coffee. How many drink both tea and coffee? Draw a Venn diagram. Are you guys getting good at your Venn diagrams? Yeah. Thanks a lot, eh? So now that we have our Venn diagram, a person is chosen at random. Find the probability that he or she, unless this is a staff of only 53 male teachers, he drinks tea but not coffee. Well, from our Venn diagram, that's the green 25, 25 out of 53. And here is our conditional probability. It's tiny. It's not always going to be underlined in green because it's grammatically incorrect to start without a capital. That's not the hint. Okay? If he is a tea drinker, what is the probability that he drinks coffee as well? So as soon as we're told that the person is a tea drinker, our world or our sample space that we're worried about reduces just to the green. How many people are in the green? 36. What is the probability he drinks coffee as well? 11 out of those 36. So what conditional probability does is it says we give you a condition, and that condition reduces your sample space. Sort of, it's just, you're just given additional information, which means you can ignore other things. We could ignore the people that don't drink coffee because we're told that we're picking a person that drinks tea. If we wanted to use our formula, this is what our formula would look like. The probability of a coffee drinker given that they're a tea drinker is equal to the probability of coffee drinker and tea drinker divided by probability of tea drinker. So here's our formula in works. So the probability of both a coffee and a tea drinker, that's that 11 in the middle. 11 out of 53 people are coffee and tea drinkers. Divided by the probability of a tea drinker is 36 out of 53. And so what the conditional probability formula does is it looks at reducing your sample space. But here we just reduced our total to 36 and said 11 out of 36. And with the conditional probability formula, it does the same thing with just thinking about probabilities. So the probability out of everybody divided by the probability of what you're looking for. If you multiply by the reciprocal, you can see that the 53s would simplify and go away. Part C. If he is a tea drinker, so again, we're out of 36. What's the probability he does not drink coffee? Well, out of those 36, there's 25 that don't drink coffee. So in this situation, I would say that our conditional probability became easier to figure out because we had the Venn diagram. And the Venn diagram very quickly allowed us to say, oh, now we're only looking at 36 people instead of looking at everybody. Find the probability that a card chosen at random from a deck of cards is the ace of spades, given that the card is black. So again, we're given some information. How does that reduce our sample space? It reduces it to 26 right away. Right? It used to be 52 cards, but you're told that it's a black card. So now you know it's 1 out of 26 cards. How many aces of spades are out of those 26? Just one. So boom. Again, we can think about this logically and come up with 1 out of 26. Formulaically, we could do it as well. What's the probability of the ace of spades given that it's black? The formula says figure out the probability of the ace of spades and black divided by the probability that it's black. Well, there's 1 out of 52 that are ace of spades. There's 26 out of 52 that are black. And if you multiply by the reciprocal, you're going to get 1 out of 26 just the same. But again, what the probability formula does is it does the probability of the event out of the whole thing divided by the probability of the condition out of the whole thing. And that's the same as being able to figure it out directly. Up till now, I would say that the logic part of you reducing the sample space has worked better. But we're going to get into some situations where the data doesn't allow us to think that way easily. It's still possible to do it that way, and I'll show you how we could do it that way. But for this one, okay, we've got a manufacturer with 3 machines to make kitchen cabinets. Machine 1 produces 40% of the cabinets because it's the best machine. Machine 2, only 25%. And what would be left is 35% for machine 3. These machines are not very good. They produce a lot of defective cabinets. So 8% of defective cabinets are produced out of machine 1. That's why it produces the most, because it's the best one. Machine 2 produces 15% defective and 10% for machine 3. So you chose a random machine, but didn't tell anyone. And then you chose a cabinet, and you find out that it's defective. But someone forgot what machine they took it from. So you're like, oh, what's the chances that it came from machine 3? So a lot of conditional probability is in this kind of context. You know something that happened now, and you want to figure out what are the events that led up to this, but you don't know what they were. And all you can do is use probability to predict what happened in the past. So we can start by drawing a tree diagram, a great way to represent everything. I've used Roman numerals I, and I for machines 1, 2, and 3, and D for defective and N for not defective. Maybe you want to use G for good. Now, if I was critiquing my own notes here, I would probably say they're okay because I knew I was going to describe to you that D stood for defective and D stood for not defective. But when you're doing this, maybe the first time you write out defective and not defective and then use your little abbreviations afterwards. Just sort of a legend, something to make it clear. Because, I mean, it could be, this one I think is pretty obvious, but maybe, is there an acronym for, or a synonym for good that starts with D? Disastrous is bad. See, all the defective ones, D words. Love in-service days. And so, what is the probability it came from machine 3? So here's where we could set up our probability formula and say we want to find the probability it came from machine 3 given that it's defective. The formula says find the probability in machine 3 and defective. Well, that would be this branch right here, which I'll highlight in yellow. Machine 3 and defective. Divided by the probability that it's defective, well, defective can come in 3 different ways, either through machine 1, machine 2, or through machine 3. So those numbers are on the bottom are adding up all of those different cases. So even though machine 3 produces the least amount of defective cabinets, there's an over 33% chance, just barely, that even though that happens, this came from machine 3. Logically, if you think about that, it makes sense because machine 3 produces that many more. So because machine 3 produces more, it's going to produce more defective ones as well, even though its percentage is lower, but its overall amount makes it that you've got a good chance, 33.5%. Part B, Now that we have our tree diagram already, if the cabinet was not defective, what is the probability it came from machine 1? So again, we can write out our Bayes formula, or conditional probability formula. We want the probability of machine 1, given that it's not defective, which means machine 1 and not defective, which I'll highlight in green, machine 1 and not defective, divided by the probability of not defective, which are those three branches. So can you see with a tree diagram, to figure out the probability of both of those events together, you're just multiplying the probabilities on each of the branches. So machine 1 and not defective, I'm taking the 0.4 on machine 1 and the 0.92 on not defective, and that's the probability of machine 1 and not defective. And add them all up, and we get our total here, which is 0.411, which apparently reduces as a fraction to 736 out of 1,791. Huh. So we figured out each of these probabilities by using the formula. That being said, you could, if you wanted to, create a situation and create a chart to figure this out. So because we're dealing with percentages here, I'm going to think of a large number. I'm going to think of, whoa, a big green dot. Oh, that might be disastrous, that erasing. Was it disastrous? Not completely disastrous. We just have one blue number we've got to figure out. I'm going to suppose we made 10,000 cabinets. And I'm going to use the percentages they gave me to figure things out. And it's good we erased one, because we really have to think about what number is going to go in there. Now, since machine 1 does 40%, 40% of 10,000, this would be the first number I would figure out, this would be the second and the third number I would figure out. Those have to add up to 10,000. Does that make sense? And I chose 10,000 because I wanted numbers that didn't end up being decimals, right? If I chose a smaller number, like 100, it might be that when I go to do 8% defective and 92% good, I have to take 8% of the 4,000. So I need a nice number that works out that way. And 8% of 4,000, or 92% of 4,000 is 3680. So just choosing an arbitrarily large number gives us good values this way. Here, with the second one is 25%. Was it 25% defective? No, 15% defective. And so 15%, I think that's 375. That was the number that was missing. And not defective would be the other 85%. So you could figure out these based on your probabilities next. And machine 3 had 10% defective. This you can really see mathematically. 10% of 3,500 is 350. And then the rest would be good. And from there, you could add up all your defective ones. Out of 10,000, there would be 1,045 defective cabinets. You have to really consider your business here. If you're doing that much problematic building, you might want to change machines completely, okay? Because just under 9,000, if you add up that whole category, will be there. Remember our first question said, given that it was defective. So now if you're thinking in terms of 10,000 cabinets, the fact that you're told that it's defective means you're choosing out of this 1,045. How many defective ones came out of machine 1? Or which one? No, question 1 was machine 3, right? That's yours, Natasha. Machine 3. Let's look. Machine 3, there was 350 defective ones out of a total of 1,045. If we take 350 divided by 1,045, let's check how close it comes to that number that we had before. And for our second question, probability, oh, here, it's ready. So 350 divided by 1,045, 33.49, exactly the same number that we would have gotten from our first question. The second one, it says it was not defective. Means out of our 10,000, we are now looking at only 8,955. What is the probability it came from machine 1? Well, 3,680 out of 8,955. If we type that in to our calculator, we get the 41%, just as we've seen. If we change that back to a fraction, it will reduce it for us to be the 736 out of 1791, which tells us that that number is exact. So I know that for me, sometimes using the conditional probability formula, even though I know that it will work out, sometimes I feel like the results are non-intuitive. Like, did I think it was going to be 41% when I read the question? I probably had no idea exactly what that number was. But if I create a chart and look at all the numbers, I find that it really makes sense when I look at the chart. Okay, I want you to try this one to start it off. I'll draw the tree diagram with you now so you can check how you did. What happens first? First serve. First serve is either, so we can label this is my first serve. It's either, what do you want to use for letters, good and bad, or in and out? Well, he hasn't won the point yet, right? He's just either served it in or out. So if he serves it in, I'll go I for in, O for out. What is his probability of serving it in? 3 out of 5. That means there's a 2 out of 5 chance that he served it out. If he serves it in, he will either win the point or lose the point. His chances of winning is 75%, or 3 out of 4. His chances of losing are 1 out of 4. If he serves it out, then he gets a second chance, which I'm going to label here as a second serve. And his second serve is either in or out. His chances of getting his second serve in, 3 out of 4, and out, 1 out of 4. If he serves it out on the second serve, I'm going to put an L in brackets because that's an automatic lose. But if he serves it in on his second serve, there's 2 possibilities. He either wins the point or loses the point. So this is a little bit more complicated tree diagram than we've seen before because some branches end earlier than others. But one of the things that we do in a tree diagram is we kind of think of a sequence of events. What happens first, then what happens after that, then what happens after that. So if the second serve is in, his probability of winning, 0.45, and probability of losing, 0.55. So what is his probability that he wins? Well, if we highlight all the branches that win, it's either this branch here or this branch here. So our probability of winning will be 3 out of 5 times 3 out of 4 plus 2/5 times 3/4 times 0.45. Someone already calculated that? I'll put it in my calculator so we have it as well. 3/5 times 3/4, that's going to be 9/20 plus 6/20 times 0.45. 0.585. Oh, I don't even need approximation signs because that's exact. So now you just went to the concession to buy a hot dog. You come back and you just see that Toby just won the point. And now you can calculate the probability that he got his first serve in without being there. Now the smart person would just ask the person next to him, did he get his first serve in? But no, you want to figure this out mathematically. So you miss the next 10 minutes of the game because you're sitting there with pencil and paper figuring this out. How can we write this using our formula? Well, we want to find the probability that we got first serve in, given that he won the point. Our formula says that is the probability of first serve in and win divided by the probability that you win. Now, of course, you can get this formula from your formula sheet, but I always remember that what's on the bottom is what you knew. Because what does conditional probability do? It reduces your sample size because it tells you something you already knew. You knew that he won the point. So working through this, what is our probability first serve in and win? Well, that is the first branch. That's 3 out of 5 times 3 out of 4. Are you all right if I just write that as 9 out of 20? And the probability that he won, you figured that out in part A, 0.585. So we can go out to our calculator. 9 divided by 20 divided by 0.585, 0.769. So you have a calculator for these, and so you have the ability to write it as a decimal, as 3 sig figs. You have the ability to write it with 3 sig figs as a percentage. You also have the ability on your calculator, math fraction, to change it as an exact answer. And then you just need an equal sign instead of the approximation sign. Okay? So every 13 times that Toby wins a point, 10 of them came from his first serve. Only 3 of them would come from his second serve.